Everyone. So let's start the afternoon session. The first speaker this afternoon is Yiannis. It's on. It's on. Oh, sorry. So let's start. The first speaker this afternoon is Yiannis Sakellaridis. He will tell us about comparison of the trace formula with Kuznetsov formula of GON and separation of the residual spectrum. Please.
Thank you very much. It is a great honor to be speaking here in this conference in honor of Jim. And it is also one of sentimental value for me to be speaking at the Fields Institute on the occasion of this conference. It's not only, I mean, maybe I'm an old person already, so I'm getting sentimental, but yesterday at dinner, I recounted how I met Jim on a one-to-one basis, how I met him and he met me. But I actually, my first encounter with Jim was during this legendary 2003 Clay summer school on automorphic forms. At the time, I was a second-year graduate student and had not yet even decided to work on the field of automorphic forms. And it was held here at the same room of the Fields Institute. It may be a little bit hard to locate Jim in the picture because it's, or anybody else, because it's very small, but it's his three heads left of Stephen. So that should make it easy. And then I returned to the Fields Institute for his 60th birthday conference that also had a big influence on me. Back to the summer school, you know, I had no idea of the big picture. I barely knew what automorphic forms are. But Jim has this amazing way to present things in a very clear and organized way and makes you think that it's simple and you can follow. And indeed, maybe you can follow line by line, but I had no idea of the big picture anyway. So that trapped me into the field, and then you spend the rest of your life hoping to understand a portion of what Jim has done. So one of my big aspirations in this life is to understand the invariant trace formula one day. Anyway, so I'm glad to be back in this room, which hasn't changed. This was not here back in the day. I don't know, for some obscure reasons, there must be some rise in patriotism recently. I was traveling a lot in the summer, but then I spent a week in the United States, so I'm glad to be back to the civilized world. Lauren and Stephen wanted me to also put a joke about King Arthur in my talk, but I'm not going to do it because, unlike the United States, this country doesn't have kings. Oh, wait.
Speaking of my great.
All right. And now let me get to math. Unfortunately, I'm not happy or proud about that, but I'm going to talk about some joint work with Chen Wan that has been for years, a few months before completion. In fact, the first calculations that led to this work were done in just before the 2017 AIM conference that Malors mentioned, and we've been working on it since then, but we haven't put enough time to. So this conference marks another deadline that we missed to finish it. Hopefully, it'll be ready in a few months. I apologize for that. It's not available yet in preprint form. So the motivation for this talk comes from at least two directions, and one is what is called beyond endoscopy. Now, beyond endoscopy is a dream of Langland's that you know, a lot of effort has been put into it in the last 25 years. We still don't really know what it is. I mean, there's still many gaps in trying to figure out even the concept of how this will work. But in any case, a lot of effort has gone into separating the Ramanujan spectrum of the trace formula from the other Arthur packets, the non-tempered Arthur packets of the trace formula. So what I'm going to talk about today has something to do with that, and Mallore's talk before also had something to do with that, as I'm sure you understood. And but I also have another piece of motivation that comes from a different direction, and it goes by the name of relative functoriality. So nowadays, functoriality applies not only to reductive groups, but also to more general spaces where groups act. You expect transfer of representations between different spaces. Spaces have their L groups. Nice spaces at least have their L groups. So you expect to be able to lift from one space to another. And lifting often happens in the form of trace formulas, or the generalization, which is the relative trace formula. And if you were able to compare relative trace formulas in more generality, you would get more relations between periods and L functions. So this is part of the motivation. So for this talk, the spaces, the relevant spaces from the point of view of the relative Langlands program are the group GLN and the Whittaker model of GLN. So on one hand, you can think of the group GLN as a two-sided GLN times GLN space. And then you can think of the Whittaker space of GLN. So G mod the maximal unipotent subgroup equipped with a non-degenerate character. So these are two different spaces for two different groups, because in the first case, I consider GLN as a GLN times GLN space. In the second case, there's only one copy of GLN acting. But roughly speaking, their spectra are comparable. Most representations appear in both. Right? So most representations, meaning most representations of GLN are generic, so they also appear in the Whittaker model. But already you can see a difference, and that difference is related to the problem of beyond nanoscopy that I mentioned. The Whittaker model only includes the Ramanujan representations. It doesn't include the residual representations. Okay. So are there any questions at this point? So I'll proceed with my next step is to give a crash course on the relative trace formula. Okay, so crash course on the relative trace formula. So let's start with the trace formula, and I'll try to convince you that the relative trace formula is a natural generalization of that. So formally, the trace formula takes a test function on a group H. So I write S of H for a space of test functions on H. You can think about CC infinity functions, or a little bit larger space, the so-called Schwarz functions, not Harish-Chandra-Schwarz, just Schwarz, so very rapid decay. So it takes a test function and computes its trace, the trace of the corresponding operator acting on the space of automorphic functions, on the L2 space of automorphic functions. Of course, in general, this is infinite, but formally that's what it does. And I'm also putting an index H here, which means co-invariance. So the output of the trace only depends on the function up to conjugation. If you conjugate the function, you're not changing the trace. So that's why the actual space of test function is a co-invariance of the usual space of test functions. It's a quotient of the usual space of test functions. Okay, so standard notation here, you can see it in the slide. Now, you could assume that your function is a convolution of two functions. In fact, the Dixmier-Malavin theorem allows you to do that with a Schwarz space. And then the corresponding convolution operator is a composition of the two convolution operators. But then the trace becomes an inner product. The trace of a composition, the trace of the composition of operators becomes the Hilbert-Schmidt inner product of the operators themselves, or maybe one, I put a star here, you have to take the adjoint of one of them. And again, formally, the Hilbert-Schmidt inner product of two operators is computed by the inner product of their kernel functions. So although we're used to seeing this form of the trace formula, where we take the kernel function and we integrate over the diagonal, you might as well rewrite it this way, where you have two test functions, and you take the L2 inner product of their kernel functions over two copies of the automorphic quotient space. It's the same thing, okay? And it is in this form that the trace formula generalizes to any pair of G spaces. So here, both of my G spaces are H. Both of my test functions lived on the group itself. Okay. I took the kernel functions which live on G, which is 2 copies of H, and I wrote down their inner product. So you can do the same with any group G and any 2 G spaces, X1 and X2. I'll give you a minute, a few seconds more to absorb this slide and ask me any questions if you have. So you can go to any pair of G spaces. You can take a test function on the product of the 2 spaces. You can take a test function on the product of the 2 spaces, or one test function on one of them and one test function on the other. You can write down the analog of the kernel function, which is this theta series, where you sum over all the rational points of your space. So this produces an automorphic function. This theta series is an automorphic function. It's the analog of the kernel. In the group case, it's really the kernel. So you have one theta series coming from the space X1, one theta series coming from the space X2, and you take the inner product of the 2 theta series, and that's what we call the relative trace formula. Formally, at least. Again, there are divergences. So this is a very flexible setup which allows you to consider both this, a lot of classical objects. So for example, when the spaces themselves are the Whittaker model, I treat the Whittaker model as a space, okay? So these are functions on G, they're not functions on G mod n, where n is the maximal unipotent. They're functions on G that vary by a generic character of n. It's a slight generalization of what I'm talking about. So when X1 and X2 are the Whittaker model, then this theta series is a very classical object that's known as the Poincaré series. If you took something else for Xi, you could end up with an Eisenstein series, for example, and things like that. So all these summations of irrational points are theta series. So the framework here is very, very, very flexible if you want to study the spectra of various spaces. So when we take the spaces to be the Whittaker model, then this kernel is known as the Poincaré series, and the relative trace formula is known as the Kuznetsov formula, or Peterson-Kuznetsov formula. Peterson first did it for holomorphic cusp forms, and the Kuznetsov formula is the generalization of this. So I will abbreviate it by KTF, Kuznetsov trace formula. Again, the Kuznetsov trace formula is the inner product of 2 Poincaré series, the same way that the usual trace formula is the inner product of 2 kernel functions. Okay. Being an inner product, at least formally again, it decomposes, it has a spectral decomposition in terms of automorphic representations. So I wrote this spectral decomposition as an integral, but you should just think about the discrete contributions for simplicity. So the Kuznetsov, when you decompose the inner product of 2 Poincaré series or any other theta series, then it's going to be a sum over all discrete automorphic representations and then some continuous integral of the projections of these series to the automorphic representation in question. Okay, and this projection to every automorphic representation is called the global relative character. Which I denote by J pi on the slide, and this is the so of course this is a distribution that depends on to which you input the test functions f1 and f2, and this is a generalization of the usual character, and because you are taking a theta series and you're projecting it to a space of an automorphic representation, this encodes integrals of automorphic forms. The automorphic forms belong to this automorphic representation pi against theta series A sub f. And these integrals can often be written as integrals over some subgroup. So in the Whittaker case, these are just the Fourier coefficients, basically. So if you integrate against the Poincaré series, you get the Fourier coefficient. So more generally, we call those periods, although they're not always periods in the sense of algebraic geometry. But this relative character encodes periods in general. And in a nice setting, these periods could be Eulerian, could have a product over all places. And when you analyze them, for example, for the Kuznetsov formula, this Euler product will give you the adjoint L function inverse at almost every place. That's for the Kuznetsov formula of GLN. So we know that the Whittaker period square factorizes, and the local factors are at almost every place. If you input the standard data and ramified data at every place, you get the inverse of the adjoint L function at 1. So here you see a significant new feature of the general RTF as opposed to the Arthur-Selberg trace formula, which is that in general you have Euler products. In the Arthur-Selberg trace formula, these Euler products are just give you 1. But in general, you have Euler products that weigh the contribution of various representations. That's one feature of the Kuznetsov formula. Specifically for the Kuznetsov formula, that's not true for the others. These Euler products are the inverse of the adjoint L function at 1. And moreover, specifically for the Kuznetsov formula, because it has to do with generic representations, because it has to do with Fourier coefficients, the residual representations of GLN do not contribute because they're not generic. So you only see the Ramanujan spectrum in the Kuznetsov formula. Are there any questions on this? So why do we care about this, about the Kuznetsov formula from the point of view of beyond endoscopy? So the goal of beyond endoscopy is to look at the stable trace formula and fish for images of functorial lifts inside of it. Find a geometric way to extract the images of functoriality from smaller groups inside of it. This is one way to summarize what the beyond endoscopy is trying to do. Langland's suggestion for how to fish for those is to fish by detecting, to organize them by the order of the pole of various L functions. Because, for example, as we've been hearing all through the conference, if the exterior square L function has a pole at s equals 1, then we understand the automorphic representation to be of symplectic type, to come from an odd orthogonal group. So this kind of phenomenon, so if you could insert L functions into the trace formula and then pick up only the representations that contribute a pole at s equals 1, that would allow you to fish for images of functoriality. Now, inserting L functions into the trace formula is not really a problem. The way you write down the L function as a Dirichlet series, you can also write a Dirichlet series of trace formulas with test functions varying in order to produce the L function that you want. Or said a little bit more adelically, you can, instead of having a standard test function, you can have a non-compactly supported test function that's designed to generate, to mimic the Dirichlet series of an L function. So this is, maybe my comment was a little bit too fast, but at least let me say that to insert an L function into the trace formula, at least in the convergent range, is not a problem for large real values of S large. That's not a problem. But the problem is that when you try to get an analytically useful expression when you go to S equals 1, things blow up before you manage to reach that point. And the reason, the reason here is the representations that are not of Ramanujan type. So it's Arthur's fault. So these representations have poles earlier than S equals 1. So you would like to remove them from the stable trace formula. Yeah, here's what I said. You want to manipulate the geometric side of the stable trace formula so that it captures the poles at S equals 1. But you first have to remove the Arthur representations. And for G equal SL2, the only representation you have to remove is the trivial representation. And this was done, well, this was removing the trivial representation. First was the object of work of Frenkel, Langlands, and Go, who suggested that we should just take Fourier transform on the space of orbital integrals, which is a one-dimensional space parameterized by the trace, and then remove the contribution of Fourier transform at 0. Altok did it rigorously for GL2 over Q, and I should have added in my slides now the very nice work of Mallors and his collaborators, who did it for more general number fields, or made progress towards doing it for more general number fields. So this is the story at this point. We're not anywhere. I don't know why Jim said that we're very close to functoriality. It doesn't feel to me that we are very close to functoriality. Maybe you had an idea that didn't fit in the margin. So, but in any case, that's the first step, and a lot of effort has been done in this direction. Now, very shortly after Langland's lecture at the Institute about beyond endoscopy, Sarnak suggested to use the Kuznetsov formula instead. That was not the only object of his letter to Langlands, but it was a basic element of his letter to Langlands, which was, if you use the Kuznetsov formula, then you don't have this problem of having to remove the contribution of the trivial representation and the other non-tempered representations, because they are not generic, so they don't appear there. And somewhat disappointingly, the motto and caricature of my talk today will be that removing the non-Ramanujan spectrum from the trace formula of GLN amounts to replacing it by the Kuznetsov formula. So I will try to argue that the process of removing the non-tempered spectrum from the from the Arthur Selberg trace formula ends up giving us the Kuznetsov formula. So let me try to say more precisely and move towards our theorem. So I will tell you that there is a certain integral operator on the space of test functions for the trace formula of GLN. By the way, in everything that I will say, I will switch from GLN to SLN. You really should be working with a stable formula for SLN. So SLN modulo GLN conjugacy. Okay, you don't gain much by thinking about the central parameter. So let's think about SLN modulo stable conjugacy, or GLN conjugacy. So then the orbital integrals for this trace formula are functions on the space of characteristic polynomials, which I think it's a little bit an unfortunate name that Langlands used in some paper, Steinberg, Hitchin base, but it's a very much more classical object. It's just the invariant theoretic quotient of G by itself. It's just the space of characteristic polynomials. So generically, orbits are parameterized by characteristic polynomials. So we think about the orbital integrals as functions defined generically on this space of orbital integrals. So I will tell you that you can take this space of test functions, or this space of orbital functions represented by their orbital integrals, and you can manipulate them by some integral transform and get functions on another affine space. Okay, so the space of characteristic polynomials for SLN is an affine space. I'll do some explicit, well, not very explicit, I'll do some integral transform on them, and this will give me a space of functions on a different affine space, which I denote by Z. And then this integral transform will satisfy some sort of Poisson summation formula, which says that the stable trace formula of F, which is roughly speaking the summation over rational orbits, I'm oversimplifying, of course, is equal to the same sum for the operator U applied to F, plus n-1 boundary terms that I'm not going to write down in any explicit way. But by doing this, we have separated the various Arthur components, namely the main term, the first sum on the right-hand side, can admit a spectral decomposition in terms of generic representations, generic automorphic representations. And the jth boundary term admits a spectral decomposition in terms of n minus j generic representations. What is an n minus j generic representation? If you think of the Arthur, I mean, I could have said it in terms of induction and residues, but let me say it in terms of Arthur parameters. If you think about a representation with Arthur parameter phi times symmetric kth power. So following the convention introduced by Arthur in his book, phi, a Langlands parameter is a Caspidal representation for some smaller general linear group. So phi here, you can think about it as some Caspidal representation into some GLM. And I'm calling M, this M, I'm calling it the generic length of the representation. So a representation is generic if and only if the sim k is trivial and the generic length is n. Okay, but we have some decomposition now where we separate the representations according to their generic length. So this is a rough caricature of the theorem. It's not precise. I'm going to try to correct it, but this is very, very roughly what the theorem wants to say. Are there any questions? Okay, so now for SL2, the orbits are parameterized just by the trace variable, the stable orbits. So the orbital integrals are functions in one variable. And this operator, this transfer operator, U, turns out to be just one-dimensional Fourier transform. The same one-dimensional Fourier transform that appears in the previously mentioned works on beyond endoscopy. More precisely, to be a little bit more precise, the operator is Fourier transform, and then you invert the variable, which means that what I call boundary terms that have to do with what happens when you apply this operator and you look at the behavior at infinity, infinity here is the zero of the Fourier transform. And that's exactly where you capture the contribution of the trivial representation. But as we will see, for higher n, if you look at SLN, the space of orbital integrals is given by an n minus 1 dimensional affine space, but the operator is not a Fourier transform on this n minus 1 dimensional affine space. The operator is some kind of iterated integral whose total dimension is n times n minus 1 over 2. So this is n minus 1 only when n is equal to 2. So for example, for SL3, the space of orbital integrals is two-dimensional, but the operator that separates the tempered and non-tempered spectrum will be a three-dimensional integral, iterated integral. Of course, otherwise it wouldn't converge. And I'll show you some formulas in low rank. But let me first say what this has to do with the Kuznetsov formula that I mentioned before. So the theorem actually tells you, I said that you go from, I said that the operator will take you from, the operator will take you from orbital integrals on G mod G. This is my symbol for the space of conjugacy classes, to some functions on some mysterious affine space Z. So now I'm telling you that this affine space Z can be identified with the space of orbital integrals for the Kuznetsov formula, the space of orbits for the Kuznetsov formula. What is the space of orbits for the Kuznetsov formula? It's the double quotient of G it's a double quotient of G by the maximal unipotent subgroup. When I put a double line here, that just means invariant theoretic quotient, spec of the invariants. Okay, so for the Kuznetsov formula, the orbital integrals look like this. We take a test function and we integrate it against two copies of, we take a test function and we integrate it against two copies of the unipotent group. That's roughly speaking what the orbital integrals look like for the Kuznetsov formula. So the space of orbital integrals is the space of n double cosets on the group. Now, again, we're going to have regular and irregular orbital integrals. So the function will not be defined everywhere on this affine space. But so for us, the regular ones will be the ones that come from the embedding of the open Broussard cell. So inside of the space of double cosets, you have the open Broussard cell. So you mod out by n on both sides, and you basically get the torus. So orbital integrals for the Kuznetsov formula are represented by the torus embedded antidiagonally. Okay, so this mysterious operator U that I denoted before will be identified as an operator that takes you from test functions on the usual trace formula to test functions on the Kuznetsov formula. And yeah, so this is the introduction to the test functions on the Kuznetsov formula. So this slide says that the orbits are parameterized by what I just told you, but there's also some extra information that one needs to keep in mind. The behavior of these orbital integrals, when you try to calculate these orbital integrals for GL2, they involve Klosterman sums at non-Archimedean places. And for GLN, we call this generalization of Klosterman sums Klosterman integrals. That's Jacquet's language. So orbital integrals here behave completely differently than they behave here. Here you have some kind of Klosterman sums appearing. Okay, any questions? So the theorem is that the operator U is actually taking you from test functions for the usual trace formula to test functions for the Kuznetsov formula, except it's not the usual space of test functions. It's a space of non-compactly supported test functions. And that's related to what I said before, that you have to introduce L functions into the trace formula. So you have to work with test functions that are not compactly supported. So another way to read the main identity that I wrote before is that after you apply this operator U, you get a Poisson summation formula that says that the stable trace formula of your original test function is equal to the Kuznetsov formula of its integral transform plus a bunch of boundary terms. The Kuznetsov formula decomposes in terms of generic representations. The boundary terms will have non-generic representations, and that's how you separated the spectrum. This is very approximate. Let me make some remarks. So first of all, why is the image of this not the usual space of test functions for the Kuznetsov formula? It couldn't. My identity could not hold with the usual space of test functions, because if you remember, every representation here contributes the inverse of the adjoint L function at 1. Every cuspidal representation here contributes the inverse of the adjoint L function at 1. While you don't see this term, this contribution here. So you have to kill it somehow. And to kill it, you need to work with this non-compactly supported space of test functions. So very naturally, what you get in the image of this map is not a standard test function. That's one thing. So this transform is like the transfer operators for usual endoscopy. It also satisfies fundamental lemma for the Hecke algebra and so on and so forth. But the fundamental lemma is not for the, it's between the standard test function for the trace formula and a non-standard test function for the Kuznetsov formula, which kills this L function in the denominator. So the actual theorem is not, like I stated before, there are huge problems that have to do with divergence. The trace formula, as we know, is not the caricature that I presented here because of divergence. So what you actually get on the left-hand side is the non-invariant trace formula. And the similar divergence appears on the Kuznetsov side because we have inserted now, we have artificially, if you want, inserted this adjoint L function at 1. This adjoint L function at 1 on the continuous spectrum has a pole at s equals 1. And this pole matches with the divergence on the trace formula side. So these two things are, these two phenomena correspond to each other. So in the end, our actual identity is between two non-invariant expressions that are somehow the residues of these poles that have to do with the, sorry, with the, so you have some expressions that depend meromorphically on some parameter s, and then you take their constant term at s equals 0, but it's not an invariant in the simple invariant form that I wrote in the previous slide. And also, last comment, this, for GL2, this one-dimensional Fourier transform that explicitly relates the trace formula to the Kuznetsov formula, for when restricted to holomorphic cusp forms, so the Kuznetsov formula is the Peterson formula, was done in 1990 by Zev Rudnik in his thesis. That was one of the things under Piatetki-Shapiro. So that was part of Rudnik's thesis, this same comparison. All right, so now what is my, I gave you a caricature of the main theorem. I don't know how much time I will have to get into details. What I want to tell you now is why I'm interested in this from the point of view of relative functoriality. And then I want to show you some formulas for the transfer operator for GL3 and GL4, or SL3 and SL4, so that you see that it's not just a simple Fourier transform. But are there any questions about the general idea of what's happening? Okay, so why should we care from the point of view of relative functoriality? Like I said, we have here two spaces. One space is the group G itself, and the other space is the group G mod n psi, so the Whittaker space. So in general, when you consider this more general setting of homogeneous spaces, G mod n psi or G mod H, where H is some subgroup of G, when you consider this general setting, as we explained before, the relative trace formula involves periods of automorphic forms over the subgroup H. So we want to study these periods, and there are very nice and general conjectures in a certain setting, spherical, blah, 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 blah. So there are very nice conjectures in some nice framework which relate these periods to special values of L functions. The most celebrated of those conjectures are the global Gann-Gross-Prasad conjectures, which were made precise, were given a precise form by Chino and Ikeda, and then in various versions of them by other people, including Lapid and Mao for the Whittaker case. Of course, for the Whittaker case of GLN, we know everything. So this for me is just a test case in order to try to move to other groups as well. So the Chino-Ikeda-Lapid-Mao conjecture for the Whittaker case tells you that this appearance of the adjoint L function inverse, when you consider squares of Whittaker periods, will also be there for more general groups. The squares of Whittaker periods for more general groups involve this factor. The conjecture is more precise than that, but so these relations between periods and L functions are have been proven in many important cases, but are largely conjectural. And what is annoying for me is that every time they're proven by using the specific features of this case, which happens to be comparable to another case that we know. So although the conjectures are very general and you know, they follow a certain. Yeah, so there is a range of conjectures of the following form. So take an automorphic representation pi and consider the period, I'm identifying it with a space of automorphic forms, and consider the period integral over some subgroup H. So pi H pi h of some automorphic form is just the integral over adelic mod rational points of h, phi of h dh. So if you make some assumptions on the space G mod h, then you can generalize the Ichino-Ikeda conjecture in the following form, that pi h squared is equal to a certain quotient of L functions. I'm not going to get into the specifics of it. But this generalization is very uniform. Okay? But we don't know how to prove this formula in general. We know how to prove it for specific cases because you can compare it with another period where you happen to know the answer. So for example, this is the Gross-Prasad, the original Gross-Prasad period. SON diagonally embedded in SON times SON plus 1. Now there's an obvious analog, which is the unitary Gross-Prasad period. So for the unitary Gross-Prasad period, the unitary group is close enough to GLN that there is an RTF comparison where Wei Zhang and then many other people, including Pierre-Henri, have proven the conjecture. But for the orthogonal case, this doesn't exist. There is another comparison that one can try for the orthogonal case, but it's a little bit problematic that we have a general conjecture and we have no general strategy for proving it. So what I have suggested is I have suggested these non-standard comparisons of relative trace formulas as a way of attacking these conjectures in general. It's still very far from this program is still in its beginnings. I've only studied rank 1 cases, but this is the first case where I'm studying a higher rank example, where I'm comparing the usual trace formula for G to the Kuznetsov formula that has to do with the Whittaker model for G. Now, this is in the case of GLN, where we know everything about the periods. But like I said, I'm interested in how this comparison would work in principle in order to try to generalize it to other cases. So that's the interest from the point of view of relative factoriality. But I have to warn you that our proof doesn't use anything beyond endoscopic. In the end, we use classical ingredients. So that may be a little bit disappointing. But again, for me, it's just a test case for how things should look like in the end. Well, I'm not doing Poisson summation directly on the space of orbital integrals. I'm doing it somewhere upstairs at the group level. I'm using a usual unfolding technique at the group level, which is very classical, and then descending it to the space of orbital integrals. It would be more desirable to have a direct proof of Poisson summation at the level of orbital integrals, but that's extremely difficult.
Why is that?
Some people are brave enough to try it. I'm not. Because in the end, the features that I'm using upstairs are very GLN-centric. They will not be reproduced for other groups. The goal would be to produce something at the level of orbital integrals directly. But at least I can see what the final formula should look like. So that's something. All right, so now let me give you formulas for the transfer operators. The formulas have been calculated by inverting the formula of Ichino and Ikeda for transfer of characters. So now, from now on, what I'm going to say is completely local. So suppose that you have some way to transfer test functions for the trace formula between test functions for the trace formula and test functions for the Kuznetsov formula. So this is my symbol for the space of test functions. Sorry, maybe here I should have put one line. Anyway, so I'm really identifying the test functions with their orbital integrals. So suppose that you have some way to transfer between those two, and this is my operator U. What are the desiderata for this transfer? The main desideratum is that it should take characters to characters. So characters are dual to test functions. So this, what is it? So here, let me write, yeah. So this was the operator U. So U star of a relative character for a Kuznetsov formula should be equal to the usual character or stable character for SLN. This is the desideratum. This is what you want your transfer to do. And for people familiar with beyond endoscopy, you should compare it with Langland singularité and transfer, where the problem was exactly this. When one group is, when we're working only with a trace formula, but one group is the torus and the other group is SL2 or GL2. So the problem of Langland's was to establish the existence of such a transfer between test functions, where here instead of Kuznetsov formula you have the torus, so that the pullback of this transfer operator will take characters of the torus to characters, the Salish-Alaika characters of the representations themselves, stable characters for SLM, for SL2. So this is the analog, but now instead of doing torus here, I'm doing Kuznetsov formula here. And the Ichino, Ikeda, Lapid, Mao formula tells us how these relative characters look like. A relative character for the Kuznetsov formula is simply the integral of the usual character for the group GLN over the unipotent group. So you take a usual character which is invariant under conjugation, you integrate it on one side under the unipotent group, and you get some generalized function which is bi-equivariant under the unipotent group. So we start from this formula for characters and we reverse engineer it to get the formula for the test functions. And we computed explicitly what this gives for low rank cases when n is up to 4. So let me give you these formulas with the caveat that already for SL2, I told you that the formula is a Fourier transform. I'm hiding some normalizing factors. So I'm not going to tell you whether I'm applying these formulas to orbital integrals or orbital integrals normalized by the discriminant or maybe the square root of the discriminant. I don't want to keep track of these details now. This is not what matters at this level. Okay, so take the details, some normalizing factors here with a grain of salt. So like we said, for n equals 2, my formulas are for the inverse operator, U inverse, okay? It goes from here to here. What does it mean that it goes from here to here? It starts with a test function for the Kuznetsov formula, which, like I said, involves some Klosterman sums. And it gives you some test function for the group. Okay. Now, like we said, for the Kuznetsov formula, you represent generically you represent your conjugacy classes by anti-diagonal torus elements. So I have some variable zeta here, and that's a parameter for the orbital integrals of the Kuznetsov formula. And then what I do is I invert the zeta, and then I take Fourier transform, and that's the inverse transfer operator. That's exactly the same formula that I said before. Okay, another way to write this is as multiplicative Fourier convolution. So you start with a test function for the Kuznetsov formula, and then in order to write its transfer in the trace variable, what you do is you do some convolution with the psi. Psi is an additive character, but you do convolution in the multiplicative group. Okay, so that's another way to write down a one-dimensional Fourier transform. The reason I'm writing it like that is that it's going to make some formulas easier for higher rank. Okay, so here's the formula for n equals 3. Like I said, for SL2, the space of orbital integrals is two-dimensional, but the transfer operator that separates the Ramanujan spectrum is given by a three-dimensional integral. And it already looks quite complicated. So this is my test function for the Kuznetsov formula. Again, I'm representing it by anti-diagonal elements. And the output is a test function for the usual trace formula, which is expressed in variables T1, T2, T3. Okay, so this is GLN. So for SLN, T3 is -1. So T1, T2, T3 are just the coefficients of the characteristic polynomial. Okay. And what does the formula look like? you do some kind of multiplicative convolution on this anti-diagonal torus. More precisely, if you look closely, you have a variable lambda1 that shows up here and here. But here it shows up in the denominator, here it shows up in the numerator. You have a variable lambda2 that shows up here and here, again, denominator, numerator. And then you have a variable mu that shows up here and here. So what is this? This looks like convolution along the three coroots. Multiplicative convolution along the three coroots. Okay? But then you see here you don't just have psi of nu plus lambda1 plus lambda2. That would be the multiplicative convolution with the psi character. You also have some additional terms that I don't really understand them, but it looks like this. You do convolution along a co-character, then you multiply by psi applied to some roots, and then you do the other two convolutions. In principle, every operation that you do satisfies Poisson summation formula, because, for example, when you take the character psi and you evaluate it, so this symbol here means you evaluate it at the sum of two roots. Anyway, whatever you're doing is something that, because the character psi is automorphic, when you sum over rational points, it vanishes. It doesn't contribute. So it's some mysterious formula like that. I don't understand it. I'm spending a lot of effort these days to understand it, but that's what it is. And let me also show you the formula for GL4 just for fun. It takes a lot of massage to bring these formulas to this form, but you see some surprising features that I find captivating. Most importantly, you see 6 convolutions, 6 multiplicative convolutions along the 6 coroots, with some fudge factors in the middle, which in principle satisfy Poisson summation, but I don't understand them. Very mysterious. But it's a 6-dimensional integral, although the space of orbits is 3-dimensional. It would be highly desirable to have a conceptual interpretation of these formulas. I have some kind of interpretation for GL2, but I have not been able to generalize it to GLN yet. But I'm an optimist. And maybe I'll sketch the proof. Like I said, are there any questions before I get there? I don't need to get to the proof, but if I have a little time, I'll get a little bit to the proof. So like I said, yes? Yeah, this is a completely local operator. This is for? No, this is an operator for test functions whose pullback, which satisfies this property for tempered representations. Yes, good point. For tempered representations. It satisfies this property. I should have said it. Very good point.
I have a general question.
Yes.
Maybe it's better to wait till the end. GL4 and sort of the regular trace formula is going to be different from GL3 in the hyperparameter. GL3 just have trivial representation. That's relevant to this, or does it complicate matters here?
This extra Arthur parameter is extra in the discrete spectrum, but already for GL3 you have extra Arthur parameter in the continuous spectrum, right? So I don't see the separation of discrete and continuous spectrum anywhere at this point.
What's the extra parameter in the continuous spectrum?
I mean, you can have, sim. You can induce from a character, right? So you can induce parabolic induction from a degenerate principal series, this kind of thing. So when I wrote before a formula with boundary terms, the boundary terms were indexed from 1 up to n-1, and they are all appear and they are all non-trivial for every n. But I'm not looking into whether they include discrete spectrum or not. Or at least it will appear in the spectral decomposition of that, but it's not. It's not something that that will appear in the transfer operator, as far as I can tell. So these Arthur packets appear when you do this transfer operator. It gives you functions that are not compactly supported, test functions that are not compactly supported. So these Arthur packets now appear somewhere at infinity, in the behavior of these test functions at infinity. And there are components at infinity, so to speak, that parameterize them. And these components exist, are indexed from 1 to n-1, irrespective of whether this includes discrete spectrum or not. Yeah, that's a degenerate principal series that I mentioned. Yeah, but it's in the continuous spectrum. It's in the continuous spectrum. Yeah. Jim was asking about the discrete spectrum. Any other questions? Okay, so like I said, the proof is using classical ingredients. It's indirect. The first ingredient is the Jacquet-Zagier trace formula, which says that, well, you can insert an Eisenstein series into the usual trace formula and try to recover the usual trace formula by taking the residue at s equals 1 of the Eisenstein series, which is, so this is a mirabolic Eisenstein series. Its residue at s equals 1 is constant. So formally, the residue of this expression at s equals 1 will give you the trace formula. And indeed, it gives you some version of the non-invariant trace formula. Why non-invariant? Because although the Eisenstein series has a simple pole at s equals 1, this expression will have a pole of order n. So that means that when I take the residue, I get something non-invariant. So that's how we start. We use this Eisenstein series. And now, but now if you introduce this Eisenstein series, you can think of it as a relative trace formula that involves the Rankin-Selberg period. And it's very well known that the Rankin-Selberg period unfolds to the Whittaker model. There's a sequence of additive Fourier transforms that takes you from the Rankin-Selberg period to the Whittaker period. And if you combine these two steps, you can get from the trace formula to the Kuznetsov formula. This is the basic idea. This same idea has also appeared in work of Liang, relatively recent work, which had other purposes in mind, the study of the Dedekind zeta function and the adjoint L function. In particular, although he had these two steps, he didn't need to study the boundary terms. So our main contribution to this argument, at least one of the main contributions, is we study the boundary terms and we show that indeed they spectrally decompose in terms of Arthur parameters of the given type. Okay, so there's a geometric way to see it that maybe I will skip, but yeah. So basically, these unfolding steps take you from a space with an action which has to do with the Rankin-Selberg methods to the Whittaker model. Maybe I'll skip this because I don't have time. But let me now correct some lies and oversimplifications, because I said that our theorem is not the exact equality that I wrote before. You should know that it cannot be the exact equality that I wrote before, because Mallours in his talk had to use the approximate functional equation to make sense of this Poisson summation formula. So we know from the previous talk that we cannot apply Poisson summation formula directly, even in the case of SL2. On the nose, we cannot do it. So I wrote down this equality, but it has to be taken with a grain of salt. So what is the actual meaning? So the actual meaning, like I said, on the left-hand side, we take the Jacquet-Zagier trace formula, and then we take its residue at s equals 1. That recovers the trace formula, but in the non-invariant form, in some non-invariant form. And then similarly, on the other side, we have the Kuznetsov formula, but for non-standard test functions, we have inserted L functions into it. These L functions have a pole in the continuous spectrum at s equals 1. That's also divergent, so again, we take a residue. So if you want, instead of instead of using the approximate functional equation to make convergent expressions, we do something similar. We deform with an S parameter. That also actually appeared in Mallo's work. I'd be interested to know what's the relation. We deform with a complex S parameter. We get an exact equality between trace formulas, which has a spectral decomposition, and then we take residues at S equals 1. There's a lot of funny things that happen here that we analyze for GL2. How do you see, for example, that in the trace formula you have discrete contribution from a part of the continuous spectrum which is invariant under the intertwining operators? So how do you see that? That's an interesting game which has to do with the poles of the L functions you see on the other side. So it's kind of fun to see these discrete contributions here. So that's all I had to say. In summary, there are transfer operators between the test functions for the Kuznetsov formula and test functions for the group, which pull back characters to, or stable characters to relative characters. After enlarging the space of test functions for the Kuznetsov formula, this becomes an isomorphism that satisfies a form of fundamental lemma. There is a deformation of the trace formula, the Jacquet-Zagier trace formula, with a parameter S, which admits a comparison with the Kuznetsov formula, and this includes boundary terms indexed from 1 to n minus 1, where the jth boundary term spectrally decomposes in terms of representations of generic length n minus j. The residue at S equals 1 gives a comparison between a version of the non-invariant trace formula and a non-invariant non-standard Kuznetsov formula with boundary terms. So you can think of this comparison as Poisson summation for the transfer operator. And finally, the transfer operator can be computed explicitly in low rank, but has not been well understood. And thank you for your attention, and thank you, Jim. Many happy returns. These are photos of Jim in Nisiros last year and this year with the members of the team who finished A25 to 27.